Okay, so then welcome to the colloquium. So today we have the pleasure of having Stefania Gori, and you know, I'm in charge of introducing her. And although you work with me in my group as a postdoc, and I'm working with her, so I know her pretty well. I ran out short of words, so I asked ChatGPT an introduction, and ChatGPT was kind enough to give me introduction in form of a poem. So I will read it. So Stefania Gori, in Italy's embrace, a mind ablaze. Stefania Gori, a physicist maze. Particle physics and cosmos, her domain, she explored the Higgs, dark matter brain. Through particle colliders and cosmic clues, she unveiled the law, uncovering new views. Dark matter, mysteries she aimed to unfold in cosmic dance, her story is told. At the unit, her PhD did bloom, as well as quest in the particle stone, with knowledge but her foundation laid, ready to venture where mysteries pervade. Both of us Argon's grand gate, and the University of Chicago to contemplate. In the hope, her brilliant thought, unraveling secrets, theory explore. Perimeter Institute has sanctuary for the world. But the cosmic wonders met her probing eyes. His abundant reflections refreshed. In an elusive essence, she thought to be traced. To Cincinnati, as assistant professor, she flew for a fleeting stay, new horizons to pursue. Guiding our minds with her interest gleam, planting seeds of curiosity in academic scheme. Now in Santa Cruz, and as associate professor, her knowledge shared an academic confessor. Particles and cosmos dancing her gaze, inspiring seekers on scientific pathways. Stefania Gori, a name revered, a physicist born, her passions steered. In the realm of particles, she's a guiding light, illuminating the cosmos with intellect bright.
Thank you, Carlos. I think it's the very first time I get an introduction like this, so pretty good start. I hope that this colloquium is at the same height of, yeah, exactly. All right, so first of all, yeah, thanks for inviting me to give this colloquium. It's a pleasure to be here to give a colloquium about my research and in general about dark matter and dark sectors. So the goal of this colloquium is to give you an overview of theory and phenomenological work that we have been doing in the last several years on dark matter and dark sectors. So since this is going to be a colloquium about particle physics, let me start a very high level. So what do we do in particle physics? We want to understand what are the fundamental elements of nature. So what is the world made of, and what holds it together? These are, of course, very old questions that we asked starting from ancient civilizations. Already at the time of ancient Greeks, people were asking these type of questions, and back then we thought that the fundamental constituents of nature were fire, air, water, and earth. Of course, we came a long way, and if you want, the starting of modern particle physics a little bit more than a century ago with the discovery of the electron by Thomson. And this discovery was followed by many other discoveries of elementary particles, as it is summarized in this cartoon. So these are all the elementary particles that we know of so far. And as you can see, each particle has two data points, sort of. So these are the dates, first of all, when the particle was first theoretized. And then afterwards, you see when it was actually discovered. And as you can see, there are particles that were discovered basically by chance. And this is the famous example of the muon that led to the famous sentence by Rabi, "Who ordered that?" So the muon discovery was completely unexpected. It was not theoretized before. then on the opposite direction, we have the discovery of the Higgs boson. And as we know, this particle was first theoretized in the 60s and then discovered in 2012 by the Large Hadron Collider. Right. Now that we have all these particles, we can finally write down the standard model for particle physics. And the summary of the standard model is just in this slide here. So we have the several particles, so matter particles and force particles that are responsible for the several interactions. The Higgs particle, two fundamental principles that are quantum mechanics and relativity. And here we have the standard model. Now, what is remarkable of this theory is that, as we see next slide, it describes very well most of the phenomena that we have measured in nature. Then also, if you think, perhaps this is a bit philosophical point, but the standard model also give us a set of universal rules, right? So these rules are lit here in Aspen, on Earth, on the moon, outside from our solar system. So we think that they are valid everywhere. And this is truly remarkable if you think about it. So we have a Lagrangian that is describing at elementary level this set of universal rules. So having said that, where are we in terms of our understanding of the standard model? With the Large Hadron Collider, we had a big success in understanding better and better this theory. The LHC gave us very, very precise measurements of standard model processes. So here in this plot, we can see a list of cross sections, so basically probabilities for these processes to happen. So this is a list of processes that are predicted by the standard model. You can see that LHC was able to measure processes, the cross section spanning many, many orders of magnitude, something like 13 orders of magnitude. The LHC was able to measure even tiny cross sections. For example, the latest one is the measurement of the four-top production at LHC. And this is really a big success that should be compared to what we knew at the beginning of the LHC, when the precision was much, much less than what we have now. And also many processes were not measured. Okay.
Question?
Yes?
What determines the size of the cross-section, the variation over this vast range?
So this gives you really probabilities. You collide protons at the LHC. The cross section gives you a measurement of probability.
I understood that. I said, what underlying feature of the model gives this vast logarithmic scale of cross sections?
Good. So if you focus on, for example, this production here, or WZ, so these are single particle production through weak interactions. Then you see that going in this direction, you go up in multiplicity. So you expect also probabilities to go down. Here we are talking about the four particle production. And also what it depends also on is what type of interactions we are describing. If there are strong interactions, weak interactions, and so on.
Thank you.
In fact, the questions are very welcome also during the
strong interactions are there.
Exactly, strong interactions are here. That's why they're much bigger. And so this I call it a big success, because we should keep in mind that particle physics is about the laws of nature. In the rest of this colloquium, we will argue that we want to discover new particles. This, of course, would be super exciting. But we have to keep in mind that particle physics is also understanding better and better interactions and properties of the particles that we have already discovered. And in this context, we see that the LHC covered a really, really important role in a better understanding of the standard model. Okay. So having said that, what is our guidance for understanding if there is more fundamental physics, if there is more elementary particles that we'll discover in the future? Theoretical guidance can come from open problems in particle physics. Some of the most important open problems are listed here. For example, the nature of dark matter, the origin of this asymmetry between the number of baryons and anti-baryons of the universe, neutrino masses, hierarchy problem, the strong CP problem. Now we are at a stage in which there is no guaranteed discovery, if you want. These are, open problems that at least give us some guidance of where to look and where we could possibly have new discoveries of particles. And for this colloquium, what I'm going to do is to focus on two of these open problems. So dark matter and strong CP problem. And argue that theories with new degrees of freedom, new particles, this mass range between KV and GV would indeed address some of these problems. Okay? So that's the goal of this colloquium. So let's see what is special about this mass range here. And first of all, let me discuss with you these two open problems, and then we'll get to this mass range afterwards. So first, the nature of dark matter. I think we don't have to argue again that we have a lot of evidence for this new form of matter coming from astrophysical and cosmological observations. Despite the fact that we have all this evidence, we don't know much about dark matter. And if it is an elementary particle, we don't know what the properties of this particle. So we know, however, that it gravitates, otherwise, we could not satisfy these observations. We know that it's dark in the sense that it doesn't interact directly with photons. It has also to be stable on cosmological scales. We know also what is its abundance. We always say that we have a lot of dark matter. In fact, we have something like 4 times more dark matter than the model matter in our universe. You can do actually a kind of acute calculation of the number of dark matter particles that you expect. There's this fun fact that if you think about the dark matter being a new particle with a mass at around 100 times the mass of the proton, you can compute and see that you would have only 1 dark matter particle per copy cap size of volume of space. But, depending on the point of view, it can be a lot or it can be not that much. Okay. Right. And also, if we focus on a framework in which dark matter is either an elementary particle or a set of elementary particles, we know that dark matter is not one of the particles of the standard model. And but however, we don't know if and how it interacts with the standard model. We will argue that we have scenarios in which we need to have some sort of interaction. But to tell the truth, we don't know if these interactions exist or not. So our role, I think, should be to test as much as you can possible interactions between dark matter and the standard model. Okay. Now, this dark matter problem motivated us to look for WIMP dark matter. So these WIMP dark matter or weakly interactive massive particle models were basically the dominant, one of the 2 dominant models for dark matter in the last couple of decades. And the reason is that these models are kind of beautiful, if you want, and simple. So let me explain how WIMP models work. Then we'll go beyond WIMP later in these slides. So how do they work? So the idea is to have a dark matter particle, a set of particles, that is interacting with a standard model at a certain level, say through the interaction of the weak forces, so through some interaction of Z bosons or Higgs bosons. And then the idea is that this dark matter is thermal in the sense that in the early universe was in thermal equilibrium with the standard model. So we had this thermal bath composed by dark matter particles and standard model particles, and we had these interactions going back and forth all the time. Okay. Then the universe continued expanding, cooling down, and then at a certain point we say that one of these interactions went out of the equilibrium, in the sense that the only efficient interactions was interaction in this direction, namely the annihilation of 2 dark matter particles to 2 standard model particles. Because of this annihilation, the density of dark matter started depleting. Okay. Then at a certain point, the universe was too big that this process of depletion shut down. This is what we call the mechanism of freeze out. But from then on, you see that the abundance just kept constant. This is the abundance that we measure now. Okay. Now, you see that this is a mechanism that is relatively simple. It just requires an interaction of dark matter with the standard model, possibly mediated by the Z or the Higgs. You can compute the abundance and compare it with the measurement. And what you see is that if dark matter has a mass at around the Higgs boson mass, leads to a type of interactions here, then you get the abundance that we have measured. Okay. This was called for a long time a WIMP miracle. We can call it coincidence, but you can agree with me that this is a beautiful framework that explains dark matter.
How did you, for this estimate, you also need to know something about the vertex?
Yeah. So here the assumption is that this interaction here is a weakly coupling strength, like the weak interactions.
Just good old weak interaction.
Right. So this is the super minimal model, just introduce WIMPs, but no, you can estimate and these numbers match if you want. So this mechanism here has motivated a large experimental endeavor to search for this type of dark matter. And in the last decade, we have reached a milestone, namely what we were able to do is to set very stringent constraints on these WIMP models. So if we put together searches that we have done at LHC, area detection, as well as astrophysical probes, we are now able to say that at least vanilla or simple WIMP models are quite totally probed. Because the level of interactions between dark matter and the standard model that we are probing is smaller than what would be required by these vanilla WIMPs. Of course, there are a lot of caveats that one should mention and keep in mind. So there are scenarios like famous Higgs, supersymmetric dark matter particle that is still viable. And actually, for those of you who were here last week, Jean-Liu gave a beautiful colloquium showing that future high energy colliders will be actually able to probe also these more hidden scenarios for WIMP dark matter. Okay. So this is where we are in terms of WIMP dark matter. So we have seen really a large and important progress in the last decade in our understanding of this framework. And before going further, I wanted also to introduce the second problem that we want to discuss during this colloquium, that is the strong CP problem. So this is a completely different problem than dark matter, even though they could be possibly connected. This is a problem of small numbers. So if you take a QCD, so the strong interactions, in principle, you can write down Lagrangian terms that are breaking CP. But then, so the CP symmetry, but then we know that we have a lot of searches for CP violation, in particular searches for electric dipole moments. If you impose the bounds from neutron electric dipole moment, you learn that this coefficient here has to be really tiny. Okay. So the question is why this coefficient is so small? And there are, again, broadly speaking, two classes of solutions to this problem. One solution rely on the fact that we are introducing a new particle that is called the QCD axion. This particle also interacts with QCD, with the strong interactions with gluons. It has a potential that is actually minimized such that this theta parameter is equal to 0. So dynamically, we are able to explain why this coefficient here is small. So we can be in agreement with experiments. Also, what is interesting of this QCD axion is that it can be dark matter candidate. So you can basically solve two problems at once. This again has motivated a lot of experimental searches, both in the lab and using astrophysical probes. So this is one of the plots that show the constraints as they are now. So if you think about this QCD axion that I presented to you in a nutshell, the mass of the axion is inversely proportional to the to 1 over FA. So it's basically proportional to the coupling of the axion with the standard model particles. So you see always lines like this. So if you want to have this minimal QCD axion model, you have to be on this line. And you see that we have several probes. All these colored regions are regions of parameter space that are already probed. Here you can see several astrophysical probes, and here there are some laboratory-based probes. We see that we are starting touching this QCD axion line. It is also quite exciting because in the future, we'll be able to do much better. So this is a study that has been done in the context of SNOWMASS, that is a community effort that took place last year, 2 years ago. We see that this QCD axion line will be covered possibly much better than what we have now. So pay attention to the scale here. So for this QCD action to work, it has to have a mass that is very light. So, you see here that it has to be below the EV scale, so much lighter scale than the WIMP dark matter that I was mentioning before. Okay. Now, how to go beyond these two frameworks? This is the question that I want to ask for this colloquium. So in general, we don't know what is the new physics scale, and in my opinion, we should be, we should try as much as we can to probe as many new physics scales as possible. Here you can see possible new physics scales ranging from very high new physics scales, 100 TeV, to very light. Here you can see the range of masses for standard model particles, so for non-elementary particles. Here you can see the range of masses where either WIMP dark matter or the QCD action can work. Okay. Then what I want to ask for this colloquium is, can we extend the range of these models, the mass range of these models? So the first question is, can I take a WIMP and make it lighter? Okay. So the WIMP idea is beautiful, as I argued. It's pretty predictive. We have tested it pretty well. Can we do something else below, say, a few GeV? The answer is yes, but with a caveat. So if we want to have a dark matter that freezes out, that is thermal and freezes out, we need also to introduce additional particles together with dark matter, because otherwise, generically, we cannot get the relic abundance that we measure. So basically, the conclusion of this is that if I want to have a light WIMP, I also need to have what I would call a dark sector, namely a sector in which we don't only have dark matter, but also some additional particle. For example, a new Z prime, a new dark photon. Okay. So thinking about WIMP models below the electroweak scale give us a good motivation for considering a physics of dark sectors. These are particles that are not charged under the standard model gauge images. Okay. Then I can ask a similar question for the QCD action. So can I go in this direction? Can I take a QCD action that is heavier than the EV scale and still solve the strong CP problem? And the answer is again yes. So there are several studies that show that in non-minimal QCD sectors, we can have actions that solve the strong CP problem that are much heavier than the EV scale. I'm reporting a plot. Of course, I'm not planning to go into the details of that. But if you look at the scales, we can have really massive QCD actions at the level of MEV or GV scale. Okay. So having said that, so I argue that we can have QCD actions that are heavier, WIMPs that are lighter. Then the question is, how do we probe these frameworks? But before going to this direction, let me give you a first intermediate summary. So what did we learn so far? So far, we learned that we have these two open problems, dark matter on one side and the strong CP problem on the other side. It could be possibly addressed by new physics, the sub-GeV scale. Okay. And the corresponding models are relatively simple, especially for dark matter. We are really reusing the idea of WIMP, just a little bit extended. And also, these new particles that we are introducing need to interact with the standard model, because otherwise we could not have, for example, this freeze out, thermal freeze out mechanism. Okay. So this is what we have learned. And for the rest of this talk, what I want to discuss with you is are the experimental probes and what are our prospects to test these scenarios. Okay. I don't know if there are questions. We're going to the second part. Otherwise, we take questions at the end. Right. So, what can we do experimentally? First of all, let me mention very broadly that in the last several years, in the last decade or so, been really a community effort in trying to understand how to test light dark sectors. And this has involved an intense collaboration of theorists and experimentalists with even the proposal of new experiments and detectors. And just a little bit of history, everything started maybe a decade ago or so with a reanalysis of past data. There was a lot of reanalysis of data taken like in the 80s or 90s. We started looking for these dark sector particles at multi-purpose experiments like the LHC or specialized smaller scale experiments. Also, DOE supported some of these proposed experiments. We talk a little bit about LDMX. This is actually not only a US-based effort, but there is a lot of activities in Europe as well. So at CERN, there is this initiative that is called the Physics Beyond Colliders, with a working group that is called Feeble Interacting Particle Physics Center. And the goal of this initiative is to understand what is the possible role of CERN in leading smaller scale experiments to test new light particles. Also, the European physics strategy for particle physics, that is a corresponding of SNOMAS in Europe, if you want, finished a couple of years ago, endorsed this type of program. Here I'm taking a sentence from the final report that says, diverse program that is complementary to the energy frontier is an essential part of the European particle physics strategy. And in fact, just for CERN, there was the proposal for many new experiments or new detectors to test the physics of light dark sectors. Okay. And last year, we had the SNOMAS process, and there was a lot of investigation of light dark sectors at small scale experiments. I was co-convening this working group with Mike Williams at MIT. Now, I want to present a few of the highlights of what we found in the last couple of years. So, first of all, since we want to test dark sectors, we need to understand how dark sectors communicate with the standard model. If they don't communicate, then we cannot have access to the dark sector. And then in terms of terms that we can write down in the Lagrangian, actually there is a relatively limited set of interactions between the dark sector and the standard model. We can start with very normalizable interactions. Here you can see the interaction, for example, of a new dark photon. It's like the photon of the standard model, but massive. And the photon of the standard model, or the interaction of a new dark scalar with the Higgs, or the interaction of a new stellar neutrino with the neutrinos of the standard model and the Higgs. And then finally, also you can see dimension 5 interactions between the axion and the several particles of the standard model. Okay. So this is at the lowest dimension, basically everything that we can write down that mediated this interaction between the dark sector and the standard model. Using these interactions, we might have hopes to have access to the physics of the dark sector. Let's see how. You want to use accelerator-based experiments. Of course, there are many other complementary ways of testing dark sectors, but for the scope of this colloquium, I will focus on accelerator-based experiments. And in this context, there are two classes of experiments. On one side, we have colliding beams, like the LHC. The very important feature of these experiments is that they can reach very, very high energies. This was, the main topic of the colloquium by you last week. Then we should not forget that we have also lower energy colliders that have a very high intensity, they're colliding a lot of particles. An example, as we'll see in a few slides, is the BEL2 experiment in Japan. It is running at much lower energies, 10 GeV equals to the 10 TeV. But nevertheless, we'll see that despite of these lower energies, thanks to the high intensity, you will be able to probe the physics of dark sector. So this is the first class of accelerator experiments. Then we have another class that are fixed target experiments. The idea is simple. We have a high intensity beam coming from here. It is scattering against some fixed target, fixed matter. Okay? Now, these experiments can reach super high intensities, higher than colliding beam experiments. But however, they cannot reach super high energies. But you can do the exercise of computing, the energy of this beam such a way to reach the same energy of the LHC, and then you would get something completely, out of mind. 100,000 of 100,000 of TeV. Okay. Now, what is interesting is that if our goal is to test like dark sectors, we don't need necessarily high energy, but we would need high intensities, especially for those dark sectors that are not coupled much to the standard model. Okay. And so the focus of this colloquium will be on understanding what these high intensity experiments can do, testing these new physics frameworks that I was introducing in the first part of this colloquium. Okay. Now, usually we highlight the discoveries of new particles at high energy colliders. So this plot here already in the colloquium by Jen. Here you can see the several colliders throughout time and the corresponding discovery of new elementary particles. The latest one here, you see the Higgs boson, the LHC. But we should also highlight that several discoveries were also done at high intensity experiments. One example is this fixed target experiment here, E288 at Fermilab, that discovered the bottom quark. Okay. So discoveries of new elementary particles were also done at fixed target high intensity experiments, so not only at high energy. Another example is the time of neutrinos. So we had plenty of examples also for this type of experiments that led to new discoveries. Okay. So what should we look for at these experiments? What are the signals that we should look for? Now, I motivated dark sectors coming from the dark matter point of view. So let's see if we follow up on this thermal freeze-out dark matter, what we learn in terms of signatures. Okay. So we have two different frameworks. So there is a first framework in which the dark matter is the lightest state of the dark sector. Okay. Then cosmologically, the only thing that can happen is that dark matter annihilates to standard model particles because of the mediation of these new particles in the dark sector. Now, you can compute processes like this, and we see that the relic abundance will be regulated by both the coupling of the dark matter in its own dark sector, and also the coupling of the dark sector with the standard model, the product of these couplings. You can compute the relic abundance, and you find the lines like this that basically tell you that the overall coupling is a sort of proportion to the mass of dark matter. Okay. I'm showing you this plot because I want to argue that if we focus on thermal freeze-out dark matter, then the coupling of the dark matter with the standard model, so this green coupling here, not be too small, because otherwise this mechanism couldn't work.
Can I ask a very dumb question? When you think of these experiments, are you running them this way or are you running them this way? Are you colliding standard model particles to get dark matter?
Great. That's a great.
Dark matter to come and picture.
That's a great question. And actually, what is very interesting is that you can look in the direction that you want. So for the relic abundance, the idea is that since we are focusing on this thermal freeze-out scenario, you have to understand how dark matter annihilates to the standard model. So you collide sort of two dark matter particles and you go to standard model. So you have to look in this direction here. Then, when we want to probe this scenario at experiments, then we'll take standard model particles and we want to produce dark matter. So we go in the opposite direction.
And they're also the symmetry allowed in the vertical direction.
That's right. Yeah. That direction I will not discuss much, but these two, absolutely, yes. All right, so this mechanism gives us a lower bound. So an experimental target that we can aim for with our present and future experiments. Okay. So this is the first type of scenario. Then we have the second scenario in which dark matter is not the lightest state, but perhaps in the dark sector, there is something that is even lighter than dark matter. And what can happen cosmologically is that the dark matter annihilates to two of these dark sector particles since they are lighter. And then the abundance will be just regulated by this coupling in the dark sector. Okay. Then you might think, okay, then how do we know how this dark matter communicates with us? We see only this coupling in blue and not the green coupling with the standard model. Actually, there is a green coupling that we need. So we need a coupling with the standard model, because I told you that we have a scenario that is thermal. To reach thermal equilibrium, we need also to have the coupling of the dark sector with the standard model. Okay. And this coupling cannot be too small, otherwise we would not thermalize in the early universe. We can compute the lower bound on this coupling. This has been done in some particular model. With this particular model, we see that the coupling smaller than, say, 10⁻⁸ wouldn't allow us to thermalize. This again to say that even for this second scenario, that is a little bit more hidden. Even in this scenario, we need to have a certain level of interaction between the dark sector and the standard model that is not too small, because otherwise this scenario wouldn't work. Again, we get an experimental target. So to summarize, so the take-home message is that we have this interesting thermal freeze-out mechanism, and that requires a specific non-zero coupling with the standard model, and therefore experimental targets that we can aim for. In terms of signals, depending on this scenario, we will have different signals at experiments. If we look at this first scenario, and again, as you were asking, we look at this diagram in this direction from right to left. What we can do is to collide standard model particles to produce dark matter. Then we have to search for some invisible signature, because dark matter is sort of invisible to our experiments. If we are in this second category, then we can produce in our experiments, again, looking in this direction, we can produce the dark sector particle. But this is lighter than dark matter, so the only thing that it can do is to decay back to the standard model. And this will lead to visible signatures that we can look for. For example, a pair of an electron and a positron, to give an example. Now let's search for these signatures. And here I'm giving you a broad overview of the experiments, accelerator-based experiments that we can use to look for these signatures. So we have the LHC, and last week talked a lot about it, so I won't mention that very much. We highlight some complementarity. Then we have light meson factories, low energy colliders, and fixed targets. And I will spend a few words on each of these type of experiments. I will conclude showing you how much we will gain our knowledge of dark sectors in the coming years. Okay. Let's start with light meson factories. Why I find this interesting? And the reason is that there are a lot of experiments, a lot of meson factories that are running now in the future, that we see a big jump in luminosity. So here I'm letting all the present and future experiments that will be producing ions that are bound states or up and down quarks or kaons or B mesons. And we see that comparing these numbers of mesons collected in the future or in the past, we have at least one order of magnitude more mesons that will be able to produce in the future. So a big jump in luminosity. Then, of course, we can use this large luminosity to test new physics, including the physics of dark sectors. I won't go into the details of all these experiments. I will mention just Pioneer and Higgs, because these are the latest experiments. So what is Pioneer? So this is an experiment that's been approved the last summer, so very recently. So this is the layout of the experiment. So this is a pion decay and rest experiment. And the idea is simple. We have a pion beam. These are pions, they go up and down quarks. We stop this pion beam here in the middle. Then we look at the product of decay of pions. Because pions are unstable. Then we look at what happened when they decay. And then pions could decay to dark sector particles, including axions. Okay. Now, usually when we show experiments in particle physics, we show these huge experiments. In the context of high intensity experiments, some of these experiments are not that big. And here for comparison, I'm putting a human. You can see this experiment is comparable to my height. Okay? So these are relatively small scale experiments. And this experiment, as I said already, it has been approved, and hopefully it will start data taking in 3-4 years. Okay. Then we have the Higgs experiment, that is a kaon decaying flight. So this is a kaon factory where kaons are bound state or down and strange. And this is a new proposal that has been put forward for CERN. This is the next generation of kaon experiments. You can find the proposal here. In super high luminosities, in principle, again, kaons can decay to dark sector particles, including Aspen. Okay. What is interesting is that using this experiment, we will be able to do new searches that have not been done in the past, and have access to models that we have not tested previously. So just to give an example, in this plot, I'm showing a model for an axion that couples to the leptons of the standard model. Now, without going into much details about this model, what I want to highlight is that the gray regions of parameter space are regions that are already probed in the past. And then you see these red and blue dashed lines are possible prospects at this Higgs pioneer experiment. We see that there are, sizable region of parameter space that we can probe. We can push, couplings by almost an order of magnitude thanks to this Higgs experiment. So of course, if nature somehow decide to give us an axion with this coupling, so if we are living here, then we could have a discovery, and if not, we can exclude this type of model. Okay. And then also what is interesting is that independent on discovery or excluding a model, we can also perform new searches. For example, this search here that we are using is a search for a kaon decaying to a positon, neutrino, and an axion. Has not been done by previous experiments. So that is exciting.
How about the results from Neutrino experiments, direct near detectors of Neutrino experiments?
I will get to that, so probably it's better to delay this conversation. Yeah. So for this particular model, they are not that relevant, but for this specific model, but there are other models that are very relevant, and we'll get into that.
Just to be sure, is the coupling GE like AE, right?
So again?
The coupling here by GE and the coupling between axion and electron.
Right. Yeah. Derivative coupling with electrons. Yeah.
How did the supernova 87A exclude that region?
So I think these are, if I remember correctly, they are cooling bounds because you can. I should look into the details again of this bound, but there can be cooling bounds, so there are bounds coming from impacting the neutrino spectrum that you get from the supernovae. Yeah. So there are plenty of this type of bounds for axion and axion particles. Right, so this is for light meson factories. Then the next type of experiments are low energy colliders. So the low energy collider that is now running is the Bell 2 experiment. So this is an experiment that is colliding positrons and electrons at high intensity. This is a collider that is done at KK in Japan, and center mass energy, so the energy of these electrons is pretty small, as we already said. This is much smaller than the energy of the LHC. And what is exciting of this experiment is that we are only at the beginning. We started a few years ago. We know that it will collect something like 100 times more luminosity than what this experiment collected already. Okay. So there will be a lot more data in the coming years. The main physics goal is to study the physics of B mesons. However, there are a lot of possibilities. Okay. Yeah. Well, here there was me visiting the lab a few months ago, if you're curious, but let's forget about it. So there are a lot of opportunities for dark sectors as well. And in fact, dark sector particles can be produced from B meson decays or also directly from the collision of E plus ions. Okay. So plenty of opportunities here, especially considering the amount of luminosity that we will collect. And in fact, there are more and more scientists in Bell 2 that are working on the physics of light dark sectors. And even the very first Bell 2 publication was a search for a new dark particle. This is a pretty new territory. In fact, the previous B factories, so we had Bell and Babar, so experiments similar to Bell 2. These B factories didn't put much resources in the direction of dark sector physics. This is really a unique opportunity for that. Okay. And And finally, the third type of experiments that I want to discuss with you are fixed targets. And so in particular, first of all, I want to ask how to produce and detect dark matter at fixed target experiments. Again, we can see the cartoon of the fixed target experiment. And interestingly enough, we can produce, because of these collisions, we can produce a dark matter beam. Okay. And the question is, how do we detect it? And there are two techniques that can be used for that. So first, technique here. So again, here we have our fixed target experiment. We produce dark matter beam. Then if you have, for example, a beam of electrons here, you produce dark matter, know that we need to conserve energy momentum, then the standard model beam will somehow be deflected. You will lose some part of its energy momentum. And if we do a measurement, an accurate measurement of this beam, we can conclude that perhaps we have produced some new particle like dark matter. Okay? This is the technique, of disappearance technique to detect dark matter. And the second technique is instead to look to try to detect this dark matter beam to the scattering in detectors. Okay. And in the coming slides, I will give you two examples of this first and second technique. I will start with LDMX, the first technique, and then I will just discuss neutrino experiments. So what is LDMX? So this is a proposed experiment for SLAC. The idea is simple, namely we start in this direction with a high intensity electron beam of a few GeV. We collide against some fixed target, and then we measure very, very accurately the beam after these collisions. And if we detect some missing momentum, that means that we have produced something invisible, perhaps dark matter, and therefore we can, set constraints or eventually discover some dark state. So this is for the first technique with this proposed experiment. Then what about the second technique? So how do we use actually neutrino experiments to discover dark matter? So first we need to understand how neutrino experiments work. Here is a schematic of a neutrino experiment. And we start with a proton beam with a high intensity. And we collide it against some target. Because of these many, many collisions, we produce a lot of mesons, for example, pions that decay to neutrinos. This is our neutrino beam. Neutrinos do not interact much with matter. So they propagate through, they can propagate through a lot of shearing through matter. Then in principle, they can scatter with our detector. And usually, these neutrino experiments have a near detector and a far detector to measure neutrino oscillations. And but what is interesting is that if we focus on this first part of the cartoon, what I can do is to replace a neutrino, this neutrino line, with a dark matter line, and everything goes very similarly. We can produce a dark matter beam that then will scatter in our near detector neutrinos. So there is this very nice synergy between the neutrino detectors and these neutrino detectors are actually dark matter detectors. Okay. So obviously, I mentioned to you a lot of experiments, but let's see how they perform. Or there are a lot of additional mesons and so on. There are a lot of different productions. Also produced directly. There are studies for a lot of different models. Yeah. So let's go back to our model. So this thermal freeze-out framework. And let's see how all the experiments that I mentioned, they perform in testing this mechanism. So here I will report just one plot, and I will give you the main messages. In this plot, what I'm showing is on the x-axis, we see the dark matter mass. As we said, now we are focusing on sub-GeV masses or so. And here on the y-axis, this is a kind of a complicated, combination of couplings and so on. You can think about it as the level of interaction between dark matter and the standard model. Okay. Now, the gray regions of parameter space are all those models that are already probed and excluded by previous experiments. So remember that a few slides ago, I showed you this thermal target. So these experimental targets, if we are on these lines here, that means that dark matter has the abundance that we have measured. Okay. So these are really the lines that we would like to probe experimentally. And we see that past experiments were not really able to probe much of these lines. But future experiments that are showed in different colors will be able to basically close all these windows, all these regions. And this is thanks to a combination of BEL2, so this low energy collider that I showed you before. Here we have neutrino experiments, and here we have the LDMX experiment. Yeah, so this, as I said, is a complicated combination of couplings, but basically, you see here, it's a product of these two couplings here, of the dark matter, its own dark sector, and with the standard model, and then some ratio of masses. So this is the effective coupling that enters in the computation of the relic abundance. Yeah.
For the study and other neutrino studies of such like dark matter, usually the assumption is necessarily through dark photon mediation. The model would be different with how LDMX can look for this thermal dark matter. So is it, could we really compare the constraints coming from LDMX?
So we can compare when we find the model, then we can compare the reads. But the comparison is model dependent. Absolutely. So this, for this specific scenario, so I since this is a colloquium, I don't plan to enter into the details, but this scenario, indeed, this is a dark photon mediated. You have a different scenario than the comparison is different between Dune and LDMX and other neutrino experiments. But overall, what is very interesting, and this is important to point out, is that putting all these experiments together, these thermal lines will be pretty broadly probed in the coming years. Yeah. So yeah, this is the conclusion, that the combination of running and proposed experiments will be able to solidly probe these minimal thermal freeze-out models. Okay. And the last topic that I wanted to discuss with you is, so far we discussed the possible production and detection of dark matter at the Higgs target. What about the other states of the dark sector? But I argue that for these models to work, we need to add also additional particles, like, for example, a dark photon. And these particles can decay back to the standard model, producing visible signatures. Then actually, fixed target experiments can also be used to detect visible signatures. You can see a cartoon here. Again, this is a fixed target experiment. You see here that there is a dump. So this is basically a block of matter that is put in this type of experiments in order to block most part of the standard model particles that just get stuck in this dump. That then afterwards, in this decay volume, main particles that we will see are just dark particles. And then if they decay back to the standard model particles will be detected by this detector that is placed afterwards. Historically, there were a lot of experiments like this running in the 80s and 90s. Here I'm collecting, most relevant ones running in the US. These were experiments either initiated by an electron beam or a proton beam. Most recently, we have, I think, only this HPS experiment at JLab that is initiated by a low energy electron beam. Also importantly, CERN also had its own program of beam dump experiments. But we see that if we look at proton beams with high energy, there is not really much anymore. So we were wondering if we can do these experiments again, and maybe with different features. And this what led us to propose a new experiment for Fermilab. So first of all, this experiment, this PinQuest experiment at Fermilab, is an existing experiment. So this is a cartoon of experiment. So this is a beam dump experiment that has access to part of the 120 GeV proton beam of Fermilab. And you can see here what is called FMAG. This is a dump of a few meters of iron. And this is an experiment that is running in the context of nuclear physics with its own nuclear physics program. But actually, if we have a dark particle decaying to muons, this is something that can be seen at this experiment, because the detector is very, very sensitive to muons. So it can identify very, very well muons. Our proposal is to take this experiment that is presently running, upgrade it, adding additional part of the detectors, like additional calorimetry, tracking layers, and so on, in such a way that we can see any visible signature. So if we have a dark particle that decays to anything that is visible, electrons, charged pions, and so on, we'll be able to see it with this upgraded experiment. This is our proposal. Now, again, we can put all the experiments together and see how we perform. And let's focus just on thermal dark sectors. That is simple. We have these experimental targets. And let's put all experiments together, again, in a minimal model where we have a dark photon. You can see the mass here of the dark photon and the interaction with the standard model. As I argued at the beginning of this colloquium, this coupling here with the standard model cannot be too small, because otherwise this framework doesn't work. I should put a line, but actually we are working in understanding exactly where the line is. It's somewhere around 10 to the minus 8, so it's somewhere around here. We need to be above this value, in such a way to have a thermal scenario. So any experiment that is probing any of this white region of parameter space is interesting in the context of this thermal model. You see that there is there are large regions of parameter space that can be probed in the future, either by running experiments like BEL2, the Dune reach, you can find it here, and here you can see dark west. Overall, we see that if we are below the GeV scale, we will be able to basically probe almost the entire region of parameter space that lead to this thermal scenario. Okay. Right, so this led to my conclusions. So in this colloquium, I wanted to argue two things. One is from the theory side, that we have new lampposts for dark matter theories and for theories addressing the CP problem. That tell us that there might be some new physics in this mass range, so sub-GeV mass range. And on the more phenomenological or experimental point of view, there is a lot of an international effort in searching for these light dark sectors. The experiments are high intensity experiments that are usually in smaller scales than high energy colliders. And there are several milestones that can be reached in a relatively short time scale in the next less than a decade or so. There is also a lot of synergy with what we can do at either high energy or with astrophysical probes. Thanks.
Okay, thank you very much, Stefania, for the beautiful talk. So then, are there questions? More questions, yes.
Yeah, so I'm convex matter theory to answer your question. But I did read this introduction of action as a solution, possible solution to strong CP problem. And I thought in that context, action should be mass-based, but you consider action with mass. So this mass is supposed to be somehow dynamically acquired, or?
Let me go back. So this is so I agree with you. So the minimal QCD action, so these are actions that have a mass that is tiny, sub EV. Okay. Then they've been, especially recently, several papers that show extended models that produce actions that are much more massive. The way that they work is basically to have an extended QCD sector, and then you have you can contribute more to the mass of these actions, and there are more than just one action.
But if they extend the QCD, give us an idea of what kind of extension. New particles with real color, or
so if you take this paper, for example, but I mean there are plenty of examples, but you can take two SU3s, okay? And the idea is that our SU3
in the standard model. I mean, it's not a dark sector.
No, you have two new SU3 at high scale, and then at some whatever new physics scale, you break this two SU3 to the diagonal one that is our SU3. Then basically the action that you get is a combination of the action for each of the SU3. And
Yeah, I had one on slide 28.
Well, it helps to find the plot. So you were probing thermal phenomena, but it sounds like they're not thermal anymore. So you made the point already later, right? So my question is, where does the model get non-thermal in this plot? So does the dark matter new initiative still probe
No, so the
matter, or do they get into the dangerous regime?
yeah, so if you focus on these lines, you are both thermal and you get the right relic abundance.
Yeah, but at some point it stops, right? So
Right.
you push it further down, and it seems that with
Yeah, but-
creative, the curve is down, but at some point you just stop. So it's interesting to see if you conclusively can test it.
Yeah, but this is, I mean,
Or if you need to go down.
yeah, for these models is pretty much lower here. For these models, as I was arguing, there are two classes of models. One is this, in which dark matter is the lightest state of the dark sector. And what you can do is to probe really the lines that produce the right relic abundance. Then there are those secluded models in which dark matter is heavier than some other particle, like a dark photon. No? Here, at that point, the standard model coupling only tells you if you are thermal or not. Okay. And here, yeah, I should put the line, but this specific dark photon model, the line of thermalization is at around 10 to the -8. So basically, this tells us that if we probe everything above roughly 10 to the -8, everywhere here in this thermal regime, below here, below 10 to the -8, we are not anymore thermal, roughly speaking.
On secluded dark matter, there's strong CMB bound.
Right. True.
Everywhere.
So it depends on the dark matter mass.
Yeah.
And so if dark matter is indeed below 10 GeV, roughly speaking, and there are very strong bounds from CMB. So if you think about a super minimal model where you have dark matter, dark photon secluded, dark matter should be roughly above 10 GeV. Then the dark photon can be much lighter than that. Okay. So what I want to say is that there are scenarios that fall into this range here that are not excluded by CMB. Clearly, you can make the dark matter more massive, and then you are more. But this is the mass of the dark photon. Yeah, I mean, from the experimental point of view, you're just looking for a dark photon decaying back to the standard model. Dark matter, you know, is you have additional parameters that you can play with. Yeah, it's true that the secluded case is more probed by CMB. Yeah.
How would detection of the neutron electron dipole moments constrain those ideas of axions and dark matter?
I mean, in general, no, this they give us the strong CP problem, right? That we need some solution of theta being small. In general.
You really don't fade into zero.
Yeah.
Is that what zero?
No.
The question is, you see a non-zero value? The question is, if we measure it.
But bigger than the standard model, I think was.
Bigger than the standard model value from.
I don't know. Whatever the standard model value is.
Yeah, it would give us information on actions. So yeah, how the dynamics of action is taking place.
But it could come from other sources. You can get the EDMs from new physics beyond the standard.
Yeah, of course. Yeah.
Nothing to do with a strong CP.
Sure. Yeah, but there are many possibilities, of course, once that you start to see a non-zero EDM. Yeah.
But I think Gordon was suggesting that if you were to see an EDM, maybe you would just forget about axions. But I think
no, okay. Yeah. Okay, I didn't, yeah. No, yeah.
No, but already, no, but just going back to that, I mean, already theta is less than whatever 10 to the -10, right?
Yeah,
I mean, what
yeah.
is explain that? So
Yeah.
I don't think, I mean, if you measured it at, I don't know, 10 to the -12 or something, that's still.
Well, but
that's
it's not,
something you want to-
not zero. That is-
It's not zero, but it's something you want to explain. And
Please.
Then, any other?
You know, so, you guys said it, the
the experiments that you described, I mean, the signals, would indicate some beyond standard model physics. Is other than the fact that those particles, beyond standard model particles would have mass, is there any other independent reason to believe they would solve these cosmological problems? Or could this missing matter, of cosmological significance simply just not talk to anything other than gravity? And this beyond standard model physics is some other important stuff that.
Absolutely, yeah. I mean, as I mentioned when I introduced the idea of dark matter, we don't know if it interacts with us with the standard model. What we can do from a experimental perspective is to try to probe as much as we can the possible interaction of dark matter with the standard model in laboratory-based experiments, and see if we can, broadly probe mechanisms for dark matter. What I find very remarkable, in my opinion, is that in the last decade, we were able to probe quite broadly with this WIMP dark matter as a mechanism for dark matter. Now we would like to do this with other lampposts that are theoretically motivated. I think we have the tools, the experimental phenomenological tools, to probe other lampposts like this thermal freeze-out dark matter. But we don't know, of course, if it is this is what is realized in nature. I don't know if that answers a little bit your question, but yeah.
So I have only one question. So in this SU3 cross SU3 scenarios, so are both thetas, 50 thetas going to zero, or eventually
Yes.
an effective EDM?
No, they're both, probably there are also models with different things, but the models that I was quoting is you put to zero the theta of each.
That goes exactly to zero.
Yeah.
Okay, so any other question? Then last question, I make
one. In the last 10 years ago, there were experiments conducted in condensed matter physics problem with certain subsector specific materials where we know there are excitations, but they do not couple to photons or magnetic field or anything, but we know they're there because any probe that we have of their free energy, we see them. And if energy is mass, one could say that a parallel has been found in condensed matter physics of dark particles with mass. And since this story that physics seems to repeat each other itself in various cases, like, there are Higgs particles in condensed matter physics, and so on. So it's amusing. And the experimentalists who have detected these and in fact confirmed these will be here in a couple of weeks.
Very good. With that kind of, that really super last question.
Last question, just to finish on a lighter note, I took you from our established chairman and asked ChatGPT to ask you a question about.
Oh man, that's a poem. Otherwise,
of course.
Okay, very good.
In hidden domains beyond our gaze lie thermal dark sectors in enigmatic haze. Tell me, wise sage, with knowledge profound, what mysteries reside in this obscure bound?
Right.